Hello and welcome to another live stream. This is for Physics 232. That's going to be electromagnetism, which is algebra and trigonometry based class for life sciences. Today we're going to talk a lot about capacitors. We're going to talk about what a capacitor is, how we determine the attributes of the capacitors, how we can talk about energy in a capacitor, and how we can actually use them in a circuit, as well as dielectric constants and other things like that. So let's start off by what is a capacitor. So a capacitor is essentially two charged plates. You can see I have two charged plates drawn on my screen here. One plate is positively charged, the other one's negatively charged, giving you kind of this uniform electric field going between them. And we know, based off of our understanding of charged plates, that the electric field outside of a charged plate, so I can say the electric field outside of any charged plate is going to be equal to theta divided by, sigma divided by 2 epsilon naught. But in this case, we actually have two electric fields out in this direction. One of them is coming from the positively charged plate going this way. The other one's going from the negatively charged plate and going the opposite way. So the total net electric field here is going to be equal to the positive sigma divided by 2 epsilon naught minus the same thing. So anytime outside of those plates, you end up with a total electric field of 0, and it cancels itself out. Now, in between those two plates, we kind of get the opposite effect, because at that point, the electric field is going in the same direction. So anywhere in this point here, our electric field is going to equal 2 times sigma over 2 epsilon naught, or just sigma over epsilon. The same is true for the other side. Of course, here the electric field is also going to be equal to 0, because those electric fields are going to cancel out in there. So with a capacitor, you have these two charged plates with a uniform electric field between them. And what changes the capacitance is the size of those plates and the distance between them. So the area of each plate, so the area in, say, meters squared, some value meter squared, and then the distance between them, determines the capacitance. So the bigger the plate is, the more capacitance it can have. The closer the plates are together, the more capacitance it has, basically. And we can define an equation or relationship is that capacitance is equal to the charge of the plates divided by the voltage potential difference between them. And for every point along these two plates, they're going to have a same potential voltage between those two. So eventually, to get the charge on there, we connect them up to kind of a circuit where this side over here is our negative side, this side over here is our positive side. Of course, I drew it backwards. This is going to be our negative side, and this is going to be our positive side. And when we connect this up to our battery or a power source or something to that effect, what happens is the positive side of the power source is going to attract all the electrons in the plates that start out neutral. So that plate becomes positively charged. And the negative side is basically going to flood electrons out to that negative side to try to get close to them, because they're attracted by the positively charged plate there. So we end up with this charged plate at that point. Before you add the battery or the power source to it, the plates start out kind of a neutral charge. And then once you add the power source to it or add the battery supply to it, then it charges that plate up. And the capacitance here we said is equal to Q over V. But if we remember that since our electric field here, this electric field is also going to be equal to Q divided by A epsilon naught in this case, because that's really, that sigma is the charge density of those plates. So plugging in the charge density for that gives us that Q over A value. So we can then kind of rearrange that equation here. And say that C, I guess I should start off also talking about voltage, or the voltage potential is equal to ED, where it's the electric field times that distance is your voltage potential. The equipotential plates that we're talking about is the voltage kind of between those 2 points. And that's going to be the same along every point of that plate. So we can plug in this value here first. So I can say that C is equal to Q over ED. And then rearranging that equation a little bit, we can solve for, where's my notes? There it is. Plugging in the Q, plugging in E, plugging this value in here to there, sorry. We end up with the capacitance is equal to the charge. Oh, the Q's are going to, Q over QA, or Q divided by A epsilon naught. And those Q's kind of cancel out. This can be multiplied by the distance still. And what we're going to end up with is this, the area times epsilon naught divided by the distance. And that's ultimately going to be what we want to define our capacitor as, because the capacitance is only really determined by the area of those plates and the distance between them. So the actual charge on the capacitor, there's a potential to have some charge on there, but the capacitance doesn't affect the charge really. It's really the charge is determined by the capacitance. And similarly, we can have some type of potential energy in those capacitors. So once those capacitors charge up, we can that charge can be stored on the capacitor, which is the main purpose of a capacitor, to really store that charge. So when you first hook it up to that circuit, the capacitor charges up and stores a charge, and we get current flowing through that circuit just to move those electrons around to get those plates charged properly. Once those plates get charged, and as they're getting charged, the current drops down and gets smaller and smaller until eventually it's zero, because those plates are fully charged. The potential energy for them, we can say, is equal to 1/2 Q times V, the charge times the voltage potential there, which is also going to be equal to 1/2 the capacitance voltage squared. And those are some of the useful relationships we have. It's really the same equation. They just moved these little relationships around with capacitance and stuff like that. So this is another really important equation, and we're going to be using those two equations to solve some problems here. So the first problem we want to look at is, what is the capacitance of a parallel plate capacitor with metal plates each of area 1 meter squared, and that are separated by 6 millimeters. So if I were to do this, we know that the capacitance is going to be equal to the area times epsilon naught divided by the distance. That's our definition of a capacitor, right? It's only determined by the area and the distance between them. So just plugging in these numbers, 1 meter squared, 0.6 millimeters, we can determine excuse me, we could determine the capacitance of this. So plugging in those values, I have 1 meter squared times epsilon naught, where epsilon naught is equal to 8.85 times 10 to the negative 12. I'm going to use the units of farad per meters. And this is a little different than what we used before. This is kind of more appropriate for the capacitor talk, because farads is the unit of capacitors, and farad is equal to a Coulomb charge divided by voltage, I believe. Yeah. So a charge divided by that voltage potential between them. So I can actually plug in my value for epsilon naught here. That's 8.85 times 10 to the negative 2 farad per meter. And we're going to divide that by 0.6 times 10 to the negative 3 meters. Okay, or 0.6 millimeters, really. So if we plug that into our calculator, we had 1 meter squared times 8.85 times 10 to the negative 12 farad per meter. I'm going to divide that whole thing by 0.6 times 10 to the negative 3 meters. And that's going to give us a value of 1.45 times 1.475 times 10 to the negative 8 farad. Which, if we were to convert that, because a lot of farads, you notice it's a really small number. Capacitance is usually in the nanofarad, microfarad range. So we can actually convert that to nanofarad and see it's 14.75 nanofarad, which nano is just times 10 to the negative 9. So we just move that decimal place one more so we can just use nanofarad instead. So this guy is going to be equal to 14.75 nanofarad. And that's a simple calculation that we can do for capacitance, taking the area times epsilon naught, dividing it by the distance. So we might ask, what charge is stored on the capacitor if the voltage is 3 kilovolts? So I mean, that's 3,000 volts is applied to this capacitor. So we know that the capacitance is 14.75 nanofarad. So we can use this relationship that we had where C is equal to Q over V, and we can use that to solve for the charge that's stored on there, because now we know the capacitance and we know the voltage. So rearranging this, we can see that Q is just equal to that capacitance times the voltage, which is going to be equal to, I'll say 1.475 times 10 to the negative 8 farad. I went back to our original definition for the math's sake. And then I'm going to multiply that by 3 times 10 to the third volts. That's 3 kilovolts there. And we're going to see what that equals there. So I still got my value here. And I'm going to multiply that times 3 times 10 to the third volts. And that gives us 0.000044 coulombs. So that's basically 4.4 times 10 to the negative fifth coulombs. So that's 4.4 times 10 to the negative fifth coulombs. Might as well move that decimal place one more to the right, because that's basically going to equal 4.4 microcoulombs, which is about standard unit of measurement for coulombs. So that's the charge on each of those plates. So you have a positive 44 microcoulombs on the positive plate, and you have a negative 44 microcoulombs on the negative plate, because those plates are going to be equal but oppositely charged to create that nice electric field and capacitance between them. Let's go to the next problem here. We have a parallel plate capacitor that has square plates and that each have a length equal to 1.4 centimeters. And they're separated by 0.7 millimeters. It is connected to a battery and charged to 11.5 volts. How much energy is stored on the capacitor? So I'm going to draw a little diagram of this one. I like drawing diagrams. It helps me visualize what's happening in the circuit. So if I have a plate, then I have another plate, and I know the distance between them. This distance here is really 0.7 millimeters between them. I know there's a voltage potential. V is equal to 11.5 volts between those two. And each of these plates has an area of 1.4 centimeters squared. That's equal to the area. So I can use these values now to try to calculate the energy that's stored in there. And we said the energy for the potential energy is equal to 1/2 times the capacitance times the voltage squared. But we have to find out first, because we know the voltage, that's given, but the capacitance can be found because that's equal to the area times epsilon naught divided by the distance. So plugging this in for C, the potential energy is going to be equal to 1/2 times that area, epsilon naught, divided by the distance, times the voltage squared. So plugging in our values now, we can say that that's equal to 1/2 times the area, which is 1.4 centimeters squared, divided by, or I guess times epsilon naught, which is 8.85 times 10 to the negative 12. Those are farads per meters. And then all divided by that distance, that 0.7, this should be millimeters, times 10 to the negative 3 meters. Put some parentheses. And we can plug that into our calculator and see what we get. So that was 1/2 times 1.4 times 10 to the negative 2, because we're in centimeters, meters. And we're going to square that value. We're going to multiply that by epsilon naught. I'm just going to use my calculator's unit conversion, constants. It has that constant stored in here. That's 8.85 times 10 to the negative 12th. Plug that in there. We're going to multiply that times 11.5 volts, and we're going to square that. I'm going to divide that whole thing by 0.7 times 10 to the negative 3 meters. And we get 1.639 times 10 to the negative 10 joules. So this is equal to 1.639 times 10 to the negative 10 joules. So it's not a lot of energy that these stored in there. It's a really close distance between them, but they're only 1.4 centimeters, so they're pretty small capacitors. Going on, we can also the next problem is to find the total capacitance for 3 capacitors connected in a series. So first we need to talk about how capacitors add up when they're in a series versus when they're in parallel, and what that means. So we're going to talk about how to use capacitors. So if we're talking about a parallel circuit, that means that we have capacitors that are connected. So this is the symbol for a capacitor. It looks like 2 plates kind of connected together. And if we have a few of those lined up where they're all connected to the same circuit on each side, this is the symbol for a battery or a power source, really a battery. That's negative, this is the positive side. Each side of this circuit is going to be the same voltage potential. So this side over here, these will all be the same positive voltage. This side down here is all the same negative voltage. And the capacitance for each of these could be different based on the spacing between them or the size of the plates for the most part. So we can label, say, this one's C1, this is C2, and this is C3 for the different capacitors. And when we add these capacitors, and this is our voltage, it's our power supply over there. When we add the capacitance up, the total capacitance is going to equal the sum of all 3 of those, C1 plus C2 plus C3. So it's a pretty easy thing to determine when they're in parallel. What happens when they're in series? Series means they're all kind of connected in line. You have one, and then that's connected to another, and that's connected to another. So in this case, I can draw it out. And we have one capacitor here, another capacitor lined up there, and another capacitor lined up there. And when this happens, so I have a negative on my positive side. So this one here is going to become positive. This one over here becomes negative. And then the inner plates in between those, they get relatively negative, positive, negative, positive. But the voltage changes between those plates. It's no longer the same voltage along each one. And that is all determined based on the capacitance for them. But we could figure out the total capacitance by adding all those values. So again, we have C1, C2, and C3. And to add up these capacitor values, the total is going to equal 1 over C1 plus 1 over C2 plus 1 over C3. And we're going to take that whole value and we're going to invert it, take it to the negative 1 power. So when we add up the reciprocal of each capacitor value and then take the reciprocal of that sum, we get the total capacitance of capacitors in a series. So that's how we can work with these problems, because this problem here is asking for the total capacitance of 3 capacitors connected in a series, given their individual capacitance of 1.5 microfarad, 2.5 microfarads, and 7.5 microfarad. So we can use that same template that we had here, copy and paste it over. Make it a little bit bigger. And now we know that, say, C1, C2, and C3, we know values for those. So this is 1.5 UF. U is like mu, so it's microfarad. 2.5 microfarad and 7.5 microfarad. So we can add up those capacitance. So the total capacitance there is going to equal 1 over 1.5 UF plus 1 over 2.5 UF plus 1 over 7.5 UF. I'm going to take that whole sum to the negative 1 power. We're just inverting it, finding the reciprocal of it, basically. And that'll tell us the total capacitance. Right? So let's do that. Pop back over to our calculator. So I'm going to actually factor out that 1 over 10 to the 6. Wrong button. So 1 over 10 to the negative 6 farad. So I'm just factoring out my microfarad units. It makes typing it in a lot easier, basically. And I can say 1 over 1.5 plus 1 over 2.5 plus 1 over 7.5. And then we're going to take this whole value now. So I'm taking it around that factored thing as well. We're going to take that to the negative 1 power. And we're going to end up with 8.33 times 10 to the negative 7 farad. 8.33 little line because it's repeating times 10 to the negative 7 farad. And if we wanted that in like a standard units, we move that decimal place 1 to the left and say it's 0.833. And that would be in microfarads now. So that's going to be the total capacitance of those 3 capacitors in a series. If they were parallel, we would just add those values up, right? And so that's a pretty easy thing to do. I'll let you do that on your own time. This problem here, we're going to suppose we have a 9.4 volt battery. and 1.6 microfarad capacitor, a 7.3 microfarad capacitor. We want to find the charge and energy stored in the capacitors connected in series. So here we're going to have to add up those capacitors in series, but we really want to find the charge and the energy that's being stored in there once we have that capacitance. So drawing my diagram out, drawing my circuit, I have a series circuit. And we're going to have 1.6 UF, 7.3 UF, and this is going to be, say, my positive, my negative, and this is a 9.4 volt battery supply. So the total capacitance we could find is going to be equal to the sum of the reciprocals of these. And we're going to take the reciprocal of that, and the reciprocal of the sum of the reciprocals. There's a lot of reciprocals. But 1 over 1.6 UF plus 1 over 7.3 UF. And we're going to take that to the negative 1 power, just to find that total capacitance. So this is, again, I'm going to factor out, just so it's a little easier, my microfarads. And then I can do 1 over 1.6 plus 1 over 7.3. And I'm going to take that whole thing to the negative 1 power to end up with 1.31 times 10 to the negative 6 farad. So that's 1.31 times 10 to the negative 6 farad, or 1.31 microfarad. So you see, by connecting those in series, all the values got smaller. They're not getting bigger when we add them in series. We're not adding capacitance to it. We're really shrinking the capacitance for them. If we were to, when we added them in parallel, we didn't calculate that. When you add them in parallel, they'd get bigger. So you would just add up all the sums of them for that. But now we want to find the charge and the energy stored in there. So let's start with the charge. Using the relationship of the capacitance is equal to the charge over voltage, we can determine what that charge is. So Q in this case is going to equal C times V, which is equal to our capacitance, the total capacitance of the circuit, times the voltage. And in this case, the voltage is 9.4 volts. So that is going to equal, just popping back to our calculator, taking the value we just have in there, multiplying it by 9.4 volts. We get 1.23 times 10 to the negative 5 coulombs. 1.23 times 10 to the negative 5 coulombs. So that is going to be our charge. So that's the charge that's on each of our capacitor plates now. The energy stored in there, we can use that potential energy that's stored is equal to 1/2 CV squared. We know the capacitance is up here. We know the voltage is 9.4. So it's just a little bit of plug and play. 1/2 is equal to, or not 1/2 is equal to, this is equal to 1/2 times 1.31 microfarad times 9.4 volts squared. Now let's see what that's equal to. So going back to our capacitance, oops, that's going to be our capacitance. And we're going to multiply that by 1/2 times our capacitance times our voltage, 9.4. And that should be volts squared. Squaring the entire thing, the 9.4 and the volts, to get this value here is 5.78, or so I guess 5.80 times 10 to the negative 5 joules. is equal to 5.80 times 10 to the negative 5 joules. That's how much energy is stored on this capacitor. So it's not too hard of a complication or equations and calculations to make. We're really focusing on these equations here. The relationship that the capacitance is equal to the charge over the voltage, and the potential energy is equal to 1/2 the capacitance times V squared. And then just that knowledge of what a capacitor is, if they give you the size and the distance, but here they're just giving us the values for them, so we just have to know how to add our capacitors together and calculate charge and potential energy from them. So if we use those same values, what is the charge and energy of the capacitors if they're connected in parallel? So here we have a parallel circuit. I had too many lines on there. I wanted to do like this, where this is our voltage supply on the left. This is still 9.4 volts. And the values for our capacitors were 1.6 and 7.3. So this is 1.6 UF, and this is 7.3 UF. Now, it doesn't matter what order any of these capacitors are, because we're just adding up the whole circuit. So we can add them up very simply as the C total is equal to 1.6 UF plus 7.3 UF, which is equal to 8.9 UF. Once we have that capacitor total, we need to find the charge and the energy that's in there, the potential energy. So the charge, just like before, Q is going to equal to CV. So taking this total capacitance, that's going to be equal to 8.9 UF times our voltage, 9.4 volts. Calculator tells us that 8.9 times 10 to the negative 6. Too many things. 8.9 times 10 to the negative 6. And this is going to be in farad times the voltage, which is 9.4 volts, is going to equal 8.4 times 10 to the negative 5 coulomb. 8.4 times 10 to the negative 5 coulomb. To find the potential energy, using that same equation, it's 1/2 CV squared, where our capacitance is still this and our voltage is still that. So we can plug those in. 1/2 times 8.9 UF times our 9.4 volts, all squared. Back to our calculator. So let's do 1/2 times, it was 8.9 times 10 to the negative 6 farad times 9.4 volts. And that would be squared. And we end up with 3.9 times 10 to the negative 4 joules. So there's the energy that's being stored in the capacitor. There's the charge on the capacitor plates when they're fully charged. And this is the capacitance, the total capacitance of those two circuits in parallel. Let's move on to the idea of dielectrics. So a dielectric is some type of polarized molecule or material whose collective electric field counters the electric field that's going in between there, in between the plates of the capacitor. So the voltage between the plates is essentially reduced, meaning that there's a smaller voltage potential for the same amount of charge that's on there. You can see that here we have basically these dipoles in here, and the negative charge are going to be attracted towards the positive charged plates, and the positive charge is going to be attracted towards the negatively charged plates, and they're going to create this electric field which is running opposite to the direction. So this is the electric field of the dipoles, and this is the electric field of the capacitor plates. And if we put too much dielectric in there, it's not going to work as well. But by lessening that, you can accumulate kind of more charge on there, so you can get this greater potential. Looking at the relationship here, C is equal to Q over V. If the I guess you have the same charge on top of it, but the voltage is now less. And since these are inversely proportional to each other, the capacitance and the voltage, as the voltage decreases, the capacitance, did I spell that right? Probably not, increases. So basically, as this voltage goes down, because there's this dielectric in there, because there's a kind of electric field that's fighting it, the capacitance is going to go up. And that's why they add dielectric in between there, because we can end up with a higher capacitance rate. We can store more energy on these capacitors using less metal, smaller plates, closer plates, and so on. So the equation for that capacitor ends up being basically the same as we had before. The area of those plates times epsilon naught divided by the distance between them. But now we multiply it by this kappa, this kind of dielectric constant. And the dielectric constant is always going to be greater than 1. Which is always greater than 1. The dielectric constant for air is basically setting that standard for 1. So if there's no dielectric in there, that's 1. And by adding some type of dielectric in there, some type of polarized molecule, it will create the capacitance to always going to go up. The capacitance of a capacitor with a dielectric compared to air is always going to be greater, because K is always going to be greater than 1. And then we calculate the capacitance basically in the same way as we did before, but now we have to add that dielectric constant into our equations. So, looking at this problem now, we have an air-filled capacitor. It's made of 2 flat parallel plates, 1.4 millimeters apart. The inside area of each plate is 7.2 centimeters squared. I want to know, what is the capacitance of the set of plates? So, we know that the capacitance is equal to kappa area epsilon naught divided by the distance between the plates. And we know that here, I'll say where the area is equal to, it says 7.2 centimeters squared. So if we convert that to meters, we get 7.00002, or sorry, 0.00072 meters squared. You always have to square that conversion between centimeters and meters as well. The distance between the plates is going to be 0.0014 meters, okay, because that's just 1.4 centimeters. And then we always have to use epsilon naught, so that's 8.85 times 10 to the negative 12 farad per meter. And then here we want an air-filled capacitor. So K, in this case, is just going to equal 1. Kappa equals 1 here. So that's the dielectric constant of air. So plugging that in, the capacitance would be equal to 1 times 7.2 times 10 to the negative 4. That's going to be a meter squared times 8.85 times 10 to the negative 12 farad per meter divided by 0.0014 meters. Looking at the units, we see that we get a little bit of cancellation here. This cancels out with that. Or no. Whoop. That cancels out with one of these. The other one cancels out with that. And our units is now going to be in farad, which is what we want. I'm plugging that into our calculator. That's 7.2 times 10 to the negative 4 in meters squared. And that was 8.85 times 10 to the negative 12 farad per meter. We're going to divide that whole value by 0.0014 meters. There we are, 4.55 times 10 to the negative 12 farad. So that's 4.55 nanofarads. 4.55 nanofarads. So like I said, capacitance is usually in very small things. When you put them in circuits, unless you're using really high voltages or something to that effect. Any of your home circuits, your remote control and stuff like that, the capacitors in there are going to be about the order of magnitude of that. About 10 to the negative 12 or in the nanofarad, microfarad range. So that is the capacitance of those plates. If the region, the same region there is or the region between the plates is filled with material whose dielectric constant is 5.7. What is the new capacitance? Well, looking at our equation up here, the only thing that changes is the value K. We're using that same capacitor, the same area of the plates, the same distance between them. Epsilon naught is a constant of the universe. We can't change that. So all we have to do is take this value here and multiply that by K, this kappa dielectric constant. So that means that C is going to equal kappa C naught, or I call this equal to C naught, the capacitance with air between there. So that's just going to equal 5.7 times 4.55 times 10 to the negative 9 farad. Just popping back over to our calculator. There it is. Grabbing that one and multiplying it by 5.7. We get 2.59 times 10 to the negative 11 farad. Oop. To I was just say 2.6 times 10 to the negative 11 farad. And that is the capacitance of that same capacitor, but now we've filled it with a dielectric that has a constant of 5.7. So you notice the difference in this. This would be, this was times 10 to the negative 12 farads. This is 10 to the negative 11. So the capacitance has actually gone up quite considerably just by adding a little bit of a dielectric. The same material is being used otherwise, just filling that air gap between those plates gives you much higher capacitance. This next problem, what is the capacitance of a parallel plate having plates of an area of 2 meters squared that are separated by 0.014 millimeters of neoprene rubber? This is giving us the K value of 6.7. So using that equation, where K is, or the capacitance is equal to kappa A epsilon naught divided by the distance between the plates, where kappa, the dielectric constant, is 6.7. The area of the plates is equal to 2 meters squared. This is a pretty big capacitor. Epsilon naught is equal to 8.85 times 10 to the negative 12 farad per meter, and it will be until someone changes the laws of physics. The distance there is 0.014 millimeters. Or I could say times 10 to the negative 3 meters. So we can calculate this capacitance, because that would be equal then to that 6.7 times 2 meters squared times 8.85 times 10 to the negative 12 farad per meter. Divide that all by 0.014 times 10 to the negative 3 meters. And that'll give us our new capacitance, or our capacitance of this capacitor. So that was 6.7 times 2 meters squared times 8.85 times 10 to the power of negative 12 farad per meter. Divide that whole thing by 0.014 times 10 to the negative 3 meters. And we get 8.47 times 10 to the negative 6 farad. Since there's 10 to the negative 6, I can write it as 8.47 microfarad. So that is going to be the capacitance of the parallel plate capacitor. So what charge does it hold when 8.5 volts is applied to it? If we apply that 8.5 volts, that's really just saying that Q is equal to CV, which comes from that relationship that the capacitance is equal to the charge divided by the voltage. So we know the capacitance is 8.47 times 10 to the negative 6 farad. When we multiply that times that 8.5 volts, this is going to equal the charge. Going back to here, we've got it there, parentheses 8.5 volts. And we're at 7.2 times 10 to the negative 5 coulombs. 7.2 times 10 to the negative 5 coulombs. And that is the charge that's on there. If we want to calculate the energy of that, we would just have to use that 1/2 CV squared, which is just going to be equal to 1/2 times that 8.47 times 10 to the negative 6 farad times our 8.5 volts squared. We could do that calculation pretty quickly as well. So that's 1/2 times, there's 8.47 times 10 to the negative 6 farad, all times 8.5 volts squared. That should give us energy, which is 3.059 times 10 to the negative 4 joules. 3.04. My brain didn't work for remembering that. 59. Say 0.059 times 10 to the negative. What factor are we at? 4 joules. So there's the energy that's stored in that capacitor. We want to compare this charge that we found in that last time to a case with no dielectric present. Well, this charge here, if we compare that to having no dielectric, we can see since the Q is equal to the capacitance times the voltage, So if I say Q naught, capacitance naught, and we'll say the voltage never changes, so it's going to be constant. And those knots are just going to be the charge and the capacitance when you have air between the capacitors. We could also say that the Q with the dielectric, QD, is going to be equal to C sub D times the voltage, where the charge with the dielectric is going to be equal to the capacitance with the dielectric divided by the voltage. So what they want to know is we're going to compare that charge. What is the charge? We're going to compare the charge with the dielectric to the charge without. So I can say QD divided by Q naught. Well, that should just be equal to C, the capacitance with the dielectric, times the voltage divided by the capacitance with air times the voltage. We have the value for the dielectric, and we can calculate the one with air pretty easily. But it's a really easy thing to see those voltages just cancel out. And the difference between these two equations, the only thing that's different than that is the dielectric here. K has that kappa of 6.7. And we had times the area epsilon naught divided by the distance. And then the bottom here, the kappa is just 1. So this is just area epsilon naught divided by the distance. All these other values are the same. The distances, the epsilon naughts, the areas, they all cancel out. The only thing here is that kappa that's going to remain. So the ratio between the charge on the plate with a dielectric divided by the charge on the plate without a dielectric is just going to equal to that dielectric constant. And that's kind of how they determine those dielectric constants. And that is the end of our live stream today. I got a form for you to fill out. If you're here, there's an attendance sheet. Make sure to fill that out to get extra credit on from your teacher, and check out our other videos from past weeks as well. Tune in next time, and I have tutoring hours through Pingy. You can make an appointment above it, but I'll drop in hours just following this. Have a great day.